So the last time that we talked, we were taking a look at carboxylic acids, and we had made the observation that regardless of whether or not they were soluble or insoluble in water, they would react with sodium hydroxide or potassium hydroxide or other types of strong bases to give water-soluble salts. Now, this is really important because part of what we're thinking about doing is our ability to both make, but then also separate carboxylic acids away from other types of functional groups. So here you can see benzoic acid, which is only slightly soluble in water. As soon as you deprotonate and remove this proton, you generate the conjugate base, which is a salt, and that's going to be soluble in water. You could also do that with ammonia, where it would function as an amine. So in this case, the nitrogen, the lone pair, is going to function as a base to take the proton away and also generate, in this case, an ammonium salt. Now, why does that matter? Well, if we had a mixture of benzyl alcohol and benzoic acid, we could dissolve both in ether. And then if we added sodium hydroxide, then in our ether layer, we would have benzyl alcohol, and we could essentially separate that away from our water layer that would be containing the sodium benzoate. And so if we wanted to isolate and purify those products, we'd be able to take advantage of the use of a separatory funnel and our two layers that are separated based on density, so the ether layer and the aqueous layer, aqueous being the water layer, and we'd be able to isolate out our benzoic acid and our benzyl alcohol. Now, why would that matter? Well, that might matter because, say for example, if we were to do a lithium aluminum hydride reduction that would take our carboxyl group to the primary alcohol, we're going to carry out that reaction in diethyl ether, some type of non-reactive aprotic solvent. You could also use THF or something else. And so we're going to get back our alcohol. And so if we wanted to be able to isolate that or separate that away, we would be able to do so. Looks like we're missing an OH group there. But the idea here is, right, you could do a reduction on a carboxylic acid, on an aldehyde. Any one of those would reduce down to a primary alcohol, and you would be able to then separate out those products. We've also talked about how catalytic hydrogenation does not reduce a carboxylic acid group. So we could use hydrogen on platinum to reduce an alkene in the presence of a carboxylic acid group. So this would be another way to be able to differentiate or to separate materials. We can also use sodium borohydride to reduce an aldehyde or a ketone in the presence of a carboxylic acid. So part of what you're starting to do are cultivate these reactions that allow you to differentiate different types of functional groups or prepare different types of functional groups. And that's going to be important because now we're starting to think about different types of reactivity and what's going to have the most reactive. The next thing we're going to look at is the preparation of esters. So esters is a functional group, if we recall, that has a carbonyl group. It has an oxygen, but now that oxygen also has an alkyl group. So in this case, an ethyl group. So we can form an ester by reacting a carboxylic acid with an alcohol in the presence of an acid. That's what's going to allow us to form an ester. And those are going to be really important because we're going to start to see several different types of esters as byproducts or metabolites associated with the carboxylic acids themselves. But it's also a way to be able to differentiate and, again, to separate out and isolate compounds. The next functional group associated with carboxylic acids that we're going to talk about is an acid halide. So this is where we have a carbonyl group that's bonded to a halogen atom. So among the acid halides, acid chlorides are by far the most common and the most widely used. So notice, if we think about our carboxylic acids, right, it's really a similar functional group to our acid halides. The only difference is instead of an OH group, now we have an X. In this case, a halogen. So that could be a chloride or a bromide or an iodide. If we look at acetyl chloride or benzoyl chloride, both of those are great examples of acid chlorides or acid halides. So how do we prepare these? Well, the easiest way to prepare them is to use something like a carboxylic acid, so in this case, butanoic acid, and your favorite reagent and mine, thionyl chloride. So that's going to react to generate butanoyl chloride, SO2, and HCl. And the last reaction mechanism that we're going to be thinking about is decarboxylation. So this is the loss of carbon dioxide from a carboxyl group. So most carboxylic acids, if they're heated to a very high temperature, undergo some type of thermal decarboxylation. Why does that matter? Well, if you think about CO2 and what we breathe out, it's not uncommon to have decarboxylation as one way that we're decomposing or breaking down metabolized like sugar, fats. So most compounds are resistant to decarboxylation. However, if you have a carboxylic acid that has a carbonyl group that is beta to the carboxyl group, well, let's take a look at that. So if we have 3-oxobutanoic acid, or acetoacetic acid, notice I have the alpha carbon. We talked about this nomenclature before, right? Alpha is the carbon that's next to our primary functional group. So alpha and then beta. So if I have a ketone or a carbonyl group beta in the beta position to my carboxylic acid, then if I do a little bit of rotating, so here, notice I rotate around this bond to flip up. Now my ketone has the ability to pull off a hydrogen. The electrons can come down, right, to form a double bond between oxygen and carbon. And then the electrons from this bond can kick up, and that's what allows us to form an enol. Remember we talked about keto and enol forms? So this is an example of the enol form. And then I can show resonance to return to, right, my keto form. If we take a look at the thermal decarboxylation of malonic acid, that's also a rearrangement of the electrons in a cyclic 6-membered transition state. So I want you to take a moment, think about how you could rearrange or convert this structure to a transition state similar to what you saw before. So if we do a rotation, right, we can see a similar 6-membered transition state. Again, the oxygen takes the hydrogen, the electrons from this bond come down to form a double bond. I then, right, break this bond to form my enol. That enol then rearranges, and I'm able to form my products, in this case, carbon dioxide, a carboxylic acid, and a carboxylic acid. That's going to be a really important piece to start thinking about, because, right, we've got one more exam that we're going to start to get ready for, and we want to make sure that we're feeling really comfortable with any one of the functional groups that we've talked about so far. So we want to be comfortable with aldehydes and with ketones, carboxylic acids, esters, acid halides, and then we want to make sure that from a mechanism standpoint, whether it's a decarboxylation or maybe it's the formation of an acid chloride, that we're comfortable drawing those mechanisms. So that's what we're going to work on for the rest of today. Hope you have a great one. We'll see you soon. Thanks again.